Today, we're going to build a simple object detection model using TensorFlow and Keras. We'll use the SAFAR10 dataset, which contains 60,032 by 32 color images in 10 classes. Let's dive right into the code. First, we need to set up the environment by installing some libraries we'll need. We're using TensorFlow, Keras, and Matplotlib. Once these libraries get installed, we import them into our script. TensorFlow is a powerful library for building and training machine learning models. Keras is a high-level API built on top of TensorFlow that makes it easier to write deep learning models. Matplotlib is a Python library for creating visualizations like charts and graphs. Next, we're loading a popular dataset called SAFAR10. This dataset contains images of 10 different object classes, like airplanes, cars, and cats. This load data function downloads and loads the dataset. It separates the data into training and testing sets. We store the images and their corresponding labels, which tell us what object is in the image, in variables named xtrain, ytrain, xtest, and ytest. Then we define a list called class names that contains the actual names of the object classes, airplane, automobile, etc. Before feeding the images into our model, we need to do some pre-processing. The pixel values in the images range from 0 to 255. We normalize them by dividing each pixel value by 255. This makes the values easier for our model to learn from. We use the toCategorical function to convert the labels from integers, 0 to 9, to a one-hot encoded format. This is a common way to represent categorical data in machine learning. Now comes the fun part, building the model. We're using a type of model called a convolutional neural network, CNN, which is very good at recognizing patterns in images. We'll build our neural network model using the sequential API from Keras. Sequential function creates a sequential model where each layer feeds into the next. This input object defines the input layer. This tells the model that it will be receiving images with a size of 32 by 32 pixels and 3 color channels, RGB. This line defines a convolutional layer with 32 filters, each with a kernel size of 3 by 3. The ReLU activation function adds nonlinearity to the layer's output. Convolutional layers help identify features in the image. Max pooling 2D defines a max pooling layer that reduces the dimensionality of the data by taking the maximum value from a 2 by 2 area. This helps reduce overfitting. We repeat these steps with 64 filters to extract more complex features. Flatten layer flattens the output of the convolutional layers into a 1D vector. This prepares the data for the fully connected layers. This dense layer defines a fully connected layer with 64 neurons and the ReLU activation function. Fully connected layers learn more complex relationships between features. And this final layer defines the output layer with 10 neurons, one for each object class, and the softmax activation function. Softmax ensures the output probabilities for all classes sum to 1. Now let's compile the model. We'll use the Atom Optimizer and categorical cross-entropy loss function. Atom Optimizer is a popular algorithm for training neural networks. The loss function measures how well the model's predictions match the true labels. And metrics tells the model to track the accuracy metric during training. Next, we'll train the model using the training data. Here's where the magic happens. We'll train for 10 epochs and use a batch size of 64. Here xtrain and ytrain are the training data. Epochs equals 10 specifies the number of times the model will go through the entire training dataset. Batch underscore size equals 64 sets the number of samples processed before updating the model's parameters. And validation underscore split holds back 20% of the training data for validation, which helps prevent overfitting. Once the model is trained, we evaluate it on the test data to see how well it performs on unseen images. This evaluate method evaluates the model on the test data and returns the loss and accuracy. We print the test accuracy to see how well the model has learned. The output shows the test accuracy of the model. This indicates how well the model is performing on the test data. A higher accuracy means the model is making more correct predictions. Let's plot the training history to visualize the model's performance over the epochs. We can plot the training history to visualize how the model's accuracy and loss changed during training. The plot shows the training and validation accuracy over the epochs. This helps us understand how the model's performance improves over time and whether it is overfitting or underfitting. Finally, we can use the trained model to make predictions on some test images. This predict method makes predictions on the first 5 test images. Here we are extracting the predicted class labels from the predictions. Then we iterate through the first 5 test images and display the image, the actual label, and the predicted label. The output shows the predicted labels for the first 5 test images. You can see how well the model is performing by comparing the predicted labels with the actual labels. And that's how you build a simple object detection model using TensorFlow and Keras. Thanks for watching. Don't forget to like, share, and subscribe for more AI Bites. If you have any questions or want to see a specific topic covered, let us know in the comments below. See you next time.